Hey, it's Dr. J. 6.4 today, graphing the logarithms. So these are the functions that we discussed yesterday. We solved a lot of equations and rewrote logarithms in other forms. And today we're going to visually see what the functions look like. I always start with the same basic logarithm, log base 2. Just like in the exponential functions, I started with 2 to the x power, and so for logarithms, I like to use the log base 2. We will expand into some other bases as we move through the material. So this is a logarithmic function. F of x equals log base 2 of x. I often just rewrite f of x as y. And so you get log base 2 of x. So this is a logarithmic function where our argument is now x. Also known as the input. So we're going to be inputting values of x, and then our output is the value y, which is technically the exponent, because what this actually means when you read this, this is what you want to think as you're doing the problems. What power of 2, because the base is 2, the output is going to be the exponent, y, and that's going to equal x. So it is exactly the opposite or the inverse of what we were talking about the other day. Yeah. So this is just what you're going to be thinking when you actually calculate the values that we're going to be putting on the graph board in a second. Let's just go ahead and start off with a good old-fashioned mother table, mother function table, x and y. Okay. Now we have to be careful here. Okay. In previous examples, I chose my x's to be -2, -1, 0, 1, and 2. In this example, I'm actually choosing my y's to be -2, -1, 0, 1, and 2. All right. So this is the inverse of the exponential base 2. In other words, the graph, you go back and look at section 6.1 and 6.2, when we were doing the exponential graphs, what used to be an x is now a y. Yeah? So these are our y's. And then I'm going to plug these y's into here, and that's going to tell me what x is. In other words, I'm solving this equation for x. Okay. So I want to know what is if y is equal to -2 here, y is equal to -2, what is the value of x? Okay. And I'm going to use this to solve. Okay. So if -2 is equal to log 2 of x, well, that means that 2 to the -2 power is equal to x. That's the definition of what a logarithm is. A logarithm is the inverse of an exponential. So that's going to be 1 over 2 squared, which is 1/4 or a quarter, 0.25. All right, do the same thing for -1. Yeah. -1, you're going to have -1 equals log base 2 of x. And I want to figure out what x is. So by definition, The definition says if log base 2 of x is -1, well then 2 to the -1 must be x. Yeah, that's the whole point of using logarithms. So that's 1 over 2, which is 0.5, 1/2. Yeah. 1 over 2 to the 1 is the same as 1/2. How about 0? So I got 0 equals log base 2 of x. So again, by definition, x is equal to 2 to the 0. So x is equal to 1. How about for 1? 1 is equal to log base 2 of x. So x is equal to 2 to the 1, which is 2. You might recognize these values. The x's today are the same as the y's from a couple days ago. For my last one, 2 equals log base 2 of x. So that means 2 squared equals x. I'm not sure if you can see that. I'll write it up here. X equals 2 squared. So x is equal to 4. Okay. So this is your mother function log table for the base 2 logarithm. What that means is any time that I want to graph a logarithm that has base 2, as long as it's base 2, this is going to be my seed. This is going to be my mother that I'm going to plant in order to grow the log function that I particularly want in that example. All right, so let's go ahead and graph this. Notice where I'm going to put my y-axis. I put it pretty far over here to the left, because there are no x's that are negative. Yeah. Notice all the x's are greater than 0. Yeah, they're all greater than 0. And just so that you have a good idea of how this works, I'm going to exaggerate my scale here. So you can clearly see everybody on here. 1, 2, 3, 4, 5, 6, 7. Let's see if I can get all the way to 8. I know there's no 8 on my chart, but I'm going to maybe throw that in at the very end, just to give an idea. Okay. So I've got x is 0.25 and y is -2. So 0.25 would be very close to the axis. For your graphs online, I wouldn't even bother with 0.25. It probably won't fit. But you can do 0.5. That one will work out pretty nicely. That's right there. 0.5 is halfway to 1. So I'm not sure if you can see the grid lines, but there's a grid line here halfway to 1. 1, 0, that's the x-intercept, 1, 0. 2, 1, so go over 2 and up 1. And 4, 2, go over 4 and up 2. And that would be my graph. Now, of course, you can get away with a little bit less work. You could probably only plot 2 of these points, but it's very difficult on paper to see 2 points making a curve, right? Typically, the human brain, when I drop my glasses, you only see 2 points, you'll see a line. It's just natural instinct. 2 points make a line. So I always graph a few more than what is required. You might wonder why I put this 8 over here. I just wanted to demonstrate that you can plot points if you choose to that are not in your mother table. The mother table is a sample, right? It's a small collection of points. You could certainly go outside of the box and do some extra points. So suppose x was equal to 8. I could just plug in 8 for x, and you could plot an extra point if you really wanted to. If you don't like any of the points from the mother table, or if they don't line up nicely, or if they don't make a good point on your graph paper, then you could make another point. So this would be what power of 2 would be equal to 8? You're trying to figure out what y is. You want to know what power of 2 is equal to 8. Well, 2 times 2 times 2 is 2 to the third, which is equal to 8. So y must be equal to 3. So even though I didn't plot it, if I really wanted to, if I was getting paid every time I plot a point, I get a bonus, I could go up here and plot one more point. So I'll take that bonus. Thank you very much. And I get a point over here where x is 8 and y is 3, and it should match with the shape of the function. Yeah. I sometimes refer to that as an insurance point. If that point doesn't connect with all the other dots, then I've definitely done something wrong. Okay. So every once in a while, especially if it's a test or something, you want to make sure it's right. Just grab another point on the graph. Why did I pick 8? Well, because 8 was a nice multiple of 2. So I wouldn't have picked 7 or 5 or anything like that. So when I say pick, you really don't have very many choices. Pick something reasonable. You'll probably make some bad choices, but you'll realize very quickly that those don't work. A couple features of this graph that I want to mention before we move on. One is the asymptote. My red pen is working. Logarithms have a vertical asymptote. The vertical asymptote is x equals 0. It means that this graph will never cross the line x equals 0. There will never be any negative x's. So this whole side is blank. Yeah, all of this side is left blank. The entire graph must live to the right of the asymptote. And then I'm going to give you your free answer for the day. The range is free. Remember a couple days ago, the domain was free. Well, that was with an exp function, an exponential function. This is a log function. So the domain used to be free for exponentials. Well, now in the logarithm, the range is free. Look, negative infinity, the y value, and this y value is going all the way to positive infinity. And so the y values are free from negative infinity to infinity. The domain is not free. The domain depends on the graph. It depends on the VA. The VA is the vertical asymptote, also known as the VA. Okay. So look for the vertical asymptote, then draw your graph. Or draw your graph, look for the vertical asymptote, and then tell me what the domain is. My pens are all dying on me today. So we'll go with example 2. Graph f of x equals negative log, I got to give it a base 2 of x plus 3. As long as it's the same base as before, you can use the base 2 mother. If the base changes, then I'm going to need a new mother function. So here's the mother function that we just had, 0.25 or 1/4, -2, 0.5 or 1/2, and -1, 1 and 0, 2 and 1, and 4 and 2. Okay. And now the whole reason why we learned transformations early on in the middle of the semester, I guess, was so that we could do it today. If you don't see a number, you see a sign here but no number, that's a -1. That's a reflector. It's going to reflect about the x-axis by multiplying all the y values by -1. So it's a reflection, a reflector. It's flipping the graph upside down. Make sure that you do the right side. Okay? If you reflect the x-axis, you multiply the y values. I can't tell you how many times I've seen people memorize x-axis and then they'll accidentally do the x values. But the x-axis is the y values. What is it, pool guy?
Come on, get over here. Sorry. Marley, get over here.
Dog's trying to eat the pool guy again. The +3 is a horizontal shift. I don't have to tell you that. It's opposite, right? So +3 means left 3. So we're going to add -3 to all the x values. So over here, I'm going to add -3 to all my x's. You can see that I'm adding -3 to all the x's. Okay. And now I'm going to go through my transformation. Let's just run down the x's first. Those will be the easiest, I think. Or actually, the y's will be easier. Let's do those first. Negative, negative, that's positive. Negative, negative, that's positive. 0, negative, that's 0. Negative times a positive, that's -1. And negative times a positive, that's -2. So this time the y's are the easy ones. The x's are not difficult. You just have to be careful. -3 plus 4, that's 1. -3 plus 2, that's -1. -3 plus 1, that's -2. You probably know what I'm going to say, the most common mistake, a sign error. Yeah, you'll get too comfortable, you'll add a negative, and you'll go the wrong direction, and you'll get the wrong value. So -2.5 and -2.75. So these are the points I'm actually going to plot. Okay. just want to decide where to put my y-axis before I... If you're doing this on a blank piece of paper, I would always recommend looking at your values before you decide where to put your axes, because you might change your mind. So notice my largest x is 1. My smallest x is negative 2.75. So notice everybody is less than greater than negative 3. All the x values are greater than negative 3. Right. I didn't really plot more points to show you this, but I could have plugged in more x's, right? And I would have got plugged in more points for x, and I would have got various values like negative 2.8, negative 2.9, negative 2.9. So this table could be much larger. I could make a much larger version of this table. And you would notice, I think it's more clear if you make a giant table. But I'm just going to draw the picture, and hopefully that will make it clear. And then I'm putting my y values 1 and 2 and negative 1 and negative 2. And again, you only have to plot the good ones. So let's go 1 and negative 2. That's definitely a good one. Here, let me move those over there. So there's 1 and negative 2. Negative 1 and negative 1. That's a good one right here. Negative 1 and negative 1. Negative 2 and 0. That's right there. Negative 2 and 0. Negative 2.5 and 1. That's right about there. Negative 2.5. There's negative 3. There's negative 2.5. There's negative 2. Okay, and I'll probably skip that one on computer, but I'll go ahead and do it on paper. The y value is 2, and the x value is getting very close to negative 3. So there's your graph. Okay. And now I've got a couple more things I need to do. I need to do the vertical asymptote, which you can kind of see it here. It's at negative 3. But I don't want to presume too much, so I'm going to go ahead and show you how to do that step by step. So next I want to find the vertical asymptote. We'll call that the VA. All you have to do is set the argument equal to 0 and solve it. Remember, the argument is a fancy way of saying whatever's inside the parentheses. We call that the arg. That's the argument. It will always be very easy to solve. I will never give you an equation that you can't solve. Or maybe I'll rephrase that. I will never give you an equation that you shouldn't already know how to solve based on your experience. So this is the vertical asymptote, negative 3. That's what we call the VA, x equals negative 3. I know, when I draw these on paper, I do it last. When you do this, you actually have to do that first. So I would watch the whole video and then start with this step. This is the first thing that you should do. So when you're drawing these on canvas, the computer requires that you draw that before you've plotted all the other dots. Okay, that's not me. That's not the way I would personally do it, but that's just the way the computer mandates that you do it. Okay. So that's for the VA. To find the domain, set the argument greater than 0. These are almost exactly the same process. You just have to remember which one's equal to and which one's greater than. All right. Asymptote is equal to, domain is greater than. So the domain is x is greater than -3. Look at the picture. Yeah, x is always greater than -3. So this side of the graph is blank. This is the blank side of the graph. There is nothing on this side of the graph. Not even the word blank side. I just wrote that for your eyes only. So this side is literally empty. All right, and then don't forget your free answer. So domain's not free, but the range is free. -infinity to infinity. Take your free answer. I'm going to be giving it away all week. I'll also put this on the final exam. Also put it on the test next week. So you're going to get lots of free answers if you take them. All right. That's the basic idea behind graphing logarithms. Now, I've only spent time with log base 2. We're going to have to move on to some other types of logarithms next. Why don't we take a break from the actual graphs and just do some algebra, just to kind of get some problems taken care of. Okay, in our next example, we're going to discuss just the concept of the vertical asymptote. And not necessarily draw the graph. This is to sort of set the tone for the future problems. When I see a logarithmic graph, the first thing I should be thinking about is where is that boundary line, that asymptote that you cannot cross. The most important piece of information probably of all the topics. I should mention that the base doesn't matter. So we have base 3. We have base E. We have base 3. We have base E. This pen is dead. Natural log is base E. If it's a visible base, well, then it is whatever it is. So this one's clearly 3. This one's E. And then remember, the common log is the one that you don't see the base. The base is 10. Okay. In all cases, regardless of base, it's always set the argument equal to 0 and solve it. So it doesn't matter what the base is. All logarithms have the same asymptote, or the same process for finding the asymptote, regardless of base. And this is what I meant in the last example when I said I'm never going to give you an equation that you can't solve. Right, or that you shouldn't already know how to solve if you're in this class. So you have 2x minus 5. You're just going to set that equal to 0 and solve it. I don't even have to show you the steps for this. If I have to show you the steps at this point, it's pointless, right? I think you can all do that. I don't think enough said there. So you have x is equal to 5 halves, or you could say 2.5, same thing. So that's your VA. X is equal to 5 halves. It's a vertical line passing through 2.5. On the graph, I actually would probably use 2.5 instead of 5 halves. All right, same idea. You're going to set the argument equal to 0 and solve it. All right, fine, I'll show the steps. I can already hear the complaining through the internet. Move the 6 to the other side, becomes -6. Divide both sides by -2. You're going to get x equals 3. This one you could probably do with mental math. X minus 4 equals 0. clearly x is equal to 4. Okay. Now here's what I'm going to do for this. We're going to get a buy one, get one free deal on this. If you find the asymptote, I'll give you a bonus question. Find the domain of each function. And I'll keep the functions the same. All right. So we have a rule for the domain. The domain rule, regardless of base, you're going to set the argument to be greater than 0. Greater than 0, not equal to 0, but greater than 0. I recommend just putting that in your list of domain rules. Yeah. So a quick summary, domain rule number 1, thou shalt not divide by 0. Good. Domain rule number 2, the radicand of an even root, in particular a square root, must be greater than or equal to 0. And then now you have domain rule number 3. Regardless of base, the argument of a logarithm is always greater than 0. Now notice we've already solved all of these. All we have to do is change our equal sign into a greater than sign, and you're going to get the same result. So the domain for A, I'm just going to abbreviate DOM, is 5/2 to infinity. The only one you need to be careful with was part B, because when you write this one out, greater than 0, you're going to divide by -2. Y'all remember this from chapter 1. When you divide by -2, you're going to reverse the alligator. And so for part B, you need to be careful. It's x is less than 3. So the domain is -infinity to 3 for part B. That's the only one you need to be careful on. For the last one, I think you could probably do it with mental math. X minus 4 is greater than 0. I saved the easiest one for last. So x is greater than 4. You could have just done that one in your head. So your domain is from 4 to infinity. Okay. I always recommend doing both of these. Domain and the vertical asymptote, they always correspond to each other. The only time you need to be careful is if you're dividing by a negative. The greater than 0 flips around and becomes less than 0. So this is the one you need to be careful about. I mean, yeah, you should be careful all the time, but you can get away with being careless, except for in this case. This is the one case that sort of forces you to pay attention to your steps. Okay, I think we have time for a couple more graphs, and then we'll be done with graphing. Let's see if my... So log base 3 of x minus 4 plus 5. We got base 3. That means we can't use the old mother function. We need to use a base 3 mother function. So what does a base 3 mother function do? Well, let me explain it. It's powers of 3 instead of powers of 2. So it's 3, 3 times 3, 3 times 3 times 3, and so on and so forth. Powers of 3. One thing you'll find that I always do is I always pick the same y values. I never change my y values. -2, -1, 0, 1, and 2. All right. These are the same x values from the previous section. So what used to be an x is now a y. Lost my pen. Okay, so what you're thinking is 3 to the y is going to give you x. So 3 to the -2 is 1 over 3 squared, which is 1/9. So that's going to be your x value. Probably won't plot 1/9 as a decimal. It's 0.1111111, or just 0.11. For -1, 3 to the -1 is 1/3, 0.33. For 0, 3 to the 0 is 1. Okay. For 1, 3 to the 1 is 3. So notice the way logarithms operate. I actually pick the y's, plug them into the exponential, and then that tells me what the logarithm is. Notice I don't actually use the logarithm. I mean, not until you become really familiar and basically an expert in algebra do I mess around with the actual function log. I always use the inverse, the exponential, because it's much easier to calculate powers than it is to calculate logs. So the last one would be 3 squared, which is 9. So this is our MF. This is our mother function. Now we're going to come back over here and do our transformations. All right, so -4, that's going to go right 4 units. Remember, opposite. And then +5, we're going to go up 5 units. So come over here, add 4 to all your x's. And then add 5 to all the y's. And if you haven't gotten good at this technique yet, you will be by the end of this chapter. And that'll be it. You'll never have to see me again, not even on the internet. All right, I'm going through my transformation. I'm going to come out over here. All transformed into a new form. Let's do the y's first. They're easy. 7, 6, 5, 4, 3. Look at that. If your y's don't come out in a nice sequence, then you definitely made some mistake. The x's are kind of all over the place. You get 13, 7, 5. What do we get here? We got 4.33. Almost read it backwards. And 4.11. So these are the points we're actually going to graph here. Couple things before I get started. Let's figure out what our vertical asymptote is. To find the VA, we're going to set x minus 4 equal to 0. You don't care about the plus 5. You don't care about the base 3. It is just the inside of the parentheses. That's called the argument. So you get x equals 4. Now combining this asymptote with these points on a piece of graph paper, we should be able to get the graph pretty nicely. I'm going to put my axis way over here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I was trying to get all the way to 13 there. Oh no. I'm not going to have room to go to 7, so just let me make a real quick modification. One, 2, 3, 4, 5, 6, 7. I want to make sure I get to 7 on the y, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 on the x. Now I know that my graph will fit. Put the vertical asymptote first. So there's your VA at 4. X equals 4. All of these points should be larger than 4. All right, let's just plot the good ones. 13 and 7, so that'll be right over here. 13 and 7, over 13 and up 7. 7 and 6, so 5, 6, 7, and 6. Right there. If you're lazy or you're in a hurry, you're just trying to get it done, you're done. That's it. You can connect the dots now if you like. The problem I have is I see 2 points. I see a straight line. I'm going to do a couple more just to make sure it comes out curved. Just to show the curvature, I like at least 3 points. It's got to turn when it hits the asymptote. On your homework, just omit the decimals. The mouse is not sensitive enough to get the decimals. Okay. The last thing that I would ask would be for the domain. That would be from 4 to infinity. And I'll still give you that free answer as well. The range, negative infinity to infinity. That's your free answer. Okay, that's about all we have time for today. If I have any graphs that I feel like need more presentation, I'll post a separate video on those. I'll call it a graphing loose ends or something like that, so watch out for that. That should basically conclude the most important examples. So until next time, Dr. Jordan, see you on the internet.